Right now, approximately 46.5 billion light-years away in every direction, lies the most mysterious boundary in existence, the edge of the observable universe, beyond which no light has ever reached us, and where the very concept of physical law begins to break down in ways that challenge everything we thought we knew about reality. This cosmic horizon doesn't mark the edge of space itself, but rather the limits of causality, information, and perhaps even the applicability of physics as we understand it. But here's what is truly mind-bending. The physics at this cosmic edge might be fundamentally different from the physics we experience in our local cosmic neighborhood. The extreme conditions near cosmic horizons, where space expands faster than light, where quantum effects might dominate on cosmic scales, where the very fabric of spacetime might transition into something unrecognizable, could reveal entirely new physical principles that govern reality beyond our observational reach. We think of physical laws as universal constants that apply throughout the cosmos. Gravity works the same way everywhere. Quantum mechanics operates identically across space. Thermodynamics governs energy relationships throughout reality. But what if this assumption is wrong? What if the physics we've discovered represents only local approximations that break down completely at cosmic boundaries where space and time themselves might not exist as we understand them? The edge of the universe presents us with the ultimate physics laboratory, where every assumption about physical reality gets tested under conditions so extreme they transcend anything achievable in earthly experiments. Here, the expansion of space itself creates horizons that fundamentally limit causality. Quantum field theory might operate in ways that create particle production from pure vacuum energy. General relativity's predictions about space-time curvature might transition into regimes where space and time become discrete rather than continuous. Recent theoretical developments in quantum gravity, string theory, and cosmology have revealed that cosmic edges might not be empty boundaries, but active physical systems where information processing, energy creation, and even consciousness itself operate according to principles that seem to violate everything we know about conservation laws and causal relationships. The holographic principle suggests that all information within any cosmic volume might be encoded on its boundary surface, making cosmic edges into cosmic hard drives containing infinite amounts of data about everything that has ever occurred within their enclosed regions. But the implications extend far beyond academic physics into fundamental questions about the nature of existence itself. If physics works differently at cosmic edges, what does this mean for the reality we experience? How do we understand scientific knowledge when it might only apply within limited cosmic domains? What happens to causality, identity, and meaning when physical law itself becomes contextual rather than universal? The observable universe horizon represents just one type of cosmic edge, the boundary beyond which electromagnetic signals cannot reach us due to the finite age of cosmic transparency. But theoretical physics predicts numerous other cosmic boundaries where different physical principles might operate. The de Sitter horizon, where cosmic acceleration creates permanent causal isolation. The black hole event horizon, where spacetime geometry becomes so extreme that classical physics breaks down. And the Planck scale, where quantum gravity effects might make space and time themselves emerge from more fundamental quantum geometric relationships. Each of these cosmic edges might represent transition zones where familiar physical laws give way to exotic physics that we can barely imagine. Near black hole horizons, the combination of extreme gravity and quantum effects might create firewalls of intense radiation, wormhole connections to other cosmic regions, or holographic information storage that preserves complete records of everything that has ever fallen past the event horizon. At cosmological horizons, the accelerating expansion of space might create particle production mechanisms that generate matter and energy from quantum vacuum fluctuations while enabling faster-than-light information transmission through quantum entanglement networks. The mathematics describing physics at cosmic edges involves some of the most advanced theoretical frameworks ever developed. Conformal field theory that describes how physical quantities behave under extreme coordinate transformations. ADS-CFT correspondence that relates gravity in cosmic interiors to quantum field theory on cosmic boundaries. And loop quantum gravity that treats space and time as discrete quantum structures rather than continuous classical fields. These mathematical frameworks predict phenomena so extraordinary they seem like science fiction. Cosmic edges that process information faster than classical computers could ever achieve. Boundaries where the flow of time becomes negotiable rather than fixed regions where consciousness itself might emerge as a fundamental feature of cosmic edge physics rather than accidental byproduct of complex information processing. Tonight, we were going to explore how the extreme conditions at cosmic boundaries might reveal entirely new physics that governs reality beyond our everyday experience. You'll discover why cosmic edges might be the most information-dense regions in the universe, how quantum effects at cosmic boundaries might create connections between widely separated cosmic regions, and why understanding edge physics might be essential for comprehending the fundamental nature of reality itself. We all journey from the observable cosmic horizon through theoretical predictions about black hole physics to speculative possibilities for physics beyond spacetime itself. You all understand how cosmic edges might serve as natural quantum computers to process cosmic information while potentially enabling consciousness to persist through cosmic transitions that would otherwise represent physical death. You will see how different cosmic edges might connect to form networks that enable information flow across cosmic scales, while creating cosmic democracy where no region possesses special status relative to cosmic edge physics. The implications extend from understanding cosmic evolution to developing technologies that might eventually enable communication across cosmic boundaries that currently seem to isolate us within our local cosmic domain. The practical applications might include quantum communication systems that exploit cosmic edge physics for faster-than-light information transmission, energy harvesting technologies that extract power from cosmic boundary processes, and computational systems that use cosmic edge information processing for calculations that would be impossible using conventional technologies. But perhaps most profound are the implications for consciousness and identity within cosmic contexts where edge physics might enable awareness to persist across cosmic transitions while connecting conscious beings to information processing networks that span cosmic scales. Your consciousness might already be participating in cosmic edge information processing through quantum effects that connect local awareness to cosmic boundary dynamics. If you're fascinated by the possibility that physics works differently at cosmic edges, that the boundaries of our universe might be active information processing systems rather than empty limits, and that understanding edge physics might reveal the fundamental computational nature of reality itself, subscribe and hit thumbs up. And here is a question that takes on new meaning when considering cosmic edge physics. If the edge of the universe processes information about everything within our cosmic domain, and if consciousness represents information processing, might the cosmic edge itself be conscious in ways we haven't yet recognized? Comment below. I'll pin the most thoughtful answer, because understanding cosmic edge physics might be understanding cosmic consciousness itself. But we're getting ahead of ourselves. To understand how physics works at the edge of the universe, we first need to understand what we mean by cosmic edges and why the boundary conditions of space itself might represent the most extreme physics laboratories in existence. Now let's begin this journey to the ultimate frontier of physics, where the laws of nature themselves might be negotiable, and where the boundaries of space and time reveal the deepest secrets about the computational structure of reality itself. Chapter 1. The Observable Universe Horizon. The most tangible cosmic edge in our experience is the observable universe horizon, a spherical boundary approximately 46.5 billion light-years away that marks the limit of electromagnetic signals that have had time to reach us since the universe became transparent to light 13.8 billion years ago. Yet this seemingly simple boundary conceals profound complexities about causality, information flow, and the fundamental limits of physical knowledge that reveal how cosmic edges operate as active information processing systems rather than passive geometric boundaries. The observable universe horizon differs fundamentally from ordinary spatial boundaries because it represents a limit imposed by the finite speed of information transmission rather than a physical barrier in space. Light travels at exactly 299,792,458 meters per second, creating an absolute speed limit for electromagnetic information transmission that determines how far into space we can observe based on how long light has been traveling since cosmic transparency began during the epoch of recombination. This cosmic transparency occurred approximately 380,000 years after the Big Bang, when the expanding universe had cooled sufficiently for electrons and protons to combine into neutral hydrogen atoms. Before recombination, space was opaque to electromagnetic radiation because free electrons scattered photons efficiently. After recombination, photons could travel freely through space for the first time, creating the cosmic microwave background radiation that fills the universe and defines our observational horizon. The mathematics of cosmic horizons involve sophisticated treatments of expanding spacetime geometry that reveal how cosmic expansion affects light propagation over cosmological distances. In an expanding universe, the distance light can travel depends not only on the speed of light and available travel time, but also on how cosmic expansion stretches space during photon transit, creating horizon distances much larger than naive calculations might suggest. The current observable universe radius of approximately 46.5 billion light-years reflects this cosmic expansion effect. Although cosmic microwave background photons began traveling toward us only 13.8 billion years ago, cosmic expansion has carried their source regions to much greater distances during their journey. This makes our observable universe much larger than would be possible in static spacetime, while creating dynamic horizon boundaries that evolve as cosmic expansion continues. The physics at the observable universe horizon becomes exotic because this boundary represents a transition zone between causally connected and causally disconnected cosmic regions. Within our observable universe, all regions have been in causal contact at some point during cosmic history, enabling information exchange and physical interaction. Beyond the horizon, cosmic regions remain permanently beyond causal contact, creating fundamental limits on information flow and physical interaction. This causal disconnection creates profound implications for understanding physical law and cosmic evolution beyond observational reach. We cannot directly verify that physical constants, natural laws, or cosmic evolution patterns continue operating identically beyond our cosmic horizon. The regions beyond our observational reach might have different fundamental parameters, alternative physical laws, or exotic cosmic evolution patterns that we cannot observe or confirm. The holographic principle, one of the most important developments in theoretical physics, suggests that all information contained within our observable universe might be encoded on the horizon boundary itself. This principle emerged from black hole thermodynamics studies, revealing that black hole entropy is proportional to boundary area rather than enclosed volume, suggesting that three-dimensional physics might emerge from two-dimensional information storage on boundary surfaces. Applied to cosmic horizons, the holographic principle implies that our observable universe as boundary surface contains complete information about everything within our cosmic domain. This cosmic hologram would encode the position, velocity, and quantum state of every particle within our observable universe while processing this information, according to physical principles that might differ fundamentally from interior physics. The information processing capacity of cosmic horizon boundaries approaches theoretical limits determined by quantum mechanics and thermodynamics. Jacob Bekenstein calculated that the maximum information storage density for any physical system equals 1 bit per quarter Planck area, making cosmic horizon surfaces into the most information-dense systems possible within known physics, while suggesting computational capabilities that exceed any conceivable conventional technology. Recent developments in the ADS-CFT correspondence have provided mathematical frameworks for understanding how physics on cosmic boundaries relates to physics within cosmic volumes. This holographic duality suggests that gravitational physics within cosmic regions corresponds precisely to quantum field theory operating on cosmic boundary surfaces, making boundary physics and interior physics two equivalent descriptions of the same underlying reality. The implications for cosmic horizon physics include possibilities for information processing, energy generation, and quantum effects that transcend conventional physical limitations. If cosmic horizons operate as quantum information processors, they might perform calculations about cosmic evolution while enabling information transmission across cosmic boundaries through quantum entanglement mechanisms that bypass classical causality constraints. Cosmic inflation theory predicts that our observable universe represents an infinitesimally small fraction of a much larger inflating cosmos, where inflation continues indefinitely in most regions while ending locally to create causally disconnected cosmic domains. This eternal inflation scenario makes our cosmic horizon boundary arbitrary rather than fundamental, representing our local observational limit rather than universal cosmic edge. The particle production mechanisms near cosmic horizons emerge from quantum field theory in curved spacetime, where the extreme spacetime curvature and acceleration near horizon boundaries can separate quantum vacuum fluctuations into real particle pairs. This Hawking radiation effect, originally discovered for black hole horizons, also applies to cosmic horizons, where cosmic acceleration creates thermal radiation that might be detectable through precision observations. The temperature of cosmic horizon radiation depends on cosmic acceleration rates and horizon curvature, typically producing extremely cold thermal radiation that would be difficult to distinguish from cosmic microwave background noise. However, future observational technologies might detect these horizon radiation signatures while providing direct evidence for exotic physics operating at cosmic boundary regions. The future evolution of our observable universe horizon will be determined by cosmic acceleration, driven by dark energy that appears to be causing exponential expansion of space. If dark energy continues driving acceleration indefinitely, our observable universe horizon will eventually begin contracting as cosmic expansion carries distant galaxies beyond our causal reach faster than new regions become observable. This cosmic horizon shrinkage would create scenarios where our observable universe becomes increasingly isolated from external cosmic regions, while approaching conditions similar to black hole interiors surrounded by event horizons. Advanced civilizations would need to develop technologies for communication across shrinking cosmic horizons or risk permanent isolation within increasingly small observable cosmic domains. The measurement of cosmic horizon properties provides opportunities for testing theoretical predictions about exotic physics while constraining cosmological parameters that determine cosmic evolution. Precision observations of cosmic microwave background radiation, galaxy distributions, and gravitational wave signals all carry information about cosmic horizon physics that can be extracted through sophisticated data analysis techniques. Future space-based observatories will enable increasingly precise measurements of cosmic horizon effects while searching for signatures of exotic physics operating at cosmic boundaries. These observations might reveal departures from conventional cosmological models that indicate new physics operating at cosmic edges, alternative cosmic geometries, or information processing mechanisms that transcend classical physical limitations. The philosophical implications of cosmic horizon physics challenge assumptions about scientific knowledge and the relationship between local experience and cosmic reality. If most of cosmic reality lies beyond our observational reach, and if physics at cosmic boundaries might differ from local physics, then science might be fundamentally limited in its ability to understand cosmic truth through local observations alone. But cosmic horizon physics also suggests that boundary regions might contain complete information about cosmic evolution through holographic information encoding, making cosmic edges into cosmic libraries that preserve complete records of cosmic history while enabling information access through advanced measurement techniques that probe boundary physics directly. The relationship between cosmic horizon physics and consciousness raises speculative possibilities about cosmic awareness operating through information processing mechanisms that span cosmic boundaries. If consciousness represents information processing, and if cosmic horizons process cosmic information, then cosmic boundaries might participate in awareness networks that extend far beyond individual biological consciousness while connecting local awareness to cosmic information processing systems. But understanding cosmic horizon physics raises immediate questions about other types of cosmic boundaries and their associated exotic physics. How do black hole event horizons relate to cosmic horizons? What happens at the Planck scale where quantum gravity effects make spacetime itself quantum mechanical? How might these different cosmic edges connect to form networks that enable information flow across cosmic scales? Chapter 2. Event Horizons and Information Firewalls. Black hole. Event horizons represent perhaps the most extreme cosmic edges accessible to current observational technology, where spacetime curvature becomes so intense that classical physics breaks down and quantum effects create phenomena that challenge every assumption about information conservation, causality, and the fundamental nature of physical reality. Recent theoretical developments suggest that event horizons might not be smooth geometric boundaries, but active information processing systems that create firewalls phenomena, wormhole connections, or holographic storage mechanisms that preserve complete information about everything that has ever crossed the horizon boundary. The classical description of event horizons, derived from Einstein's general relativity, treats them as geometric surfaces surrounding black holes where the escape velocity equals the speed of light. From this classical perspective, event horizons appear as one-way membranes that allow matter and information to fall inward while preventing any signals from escaping to external observers. This geometric picture suggested that information falling into black holes becomes permanently inaccessible, creating apparent violations of quantum mechanical unitarity. However, Stephen Hawking's discovery that black holes emit thermal radiation revolutionized our understanding of event horizon physics by revealing quantum effects that make black holes behave as thermal objects with well-defined temperatures and entropies. Hawking radiation emerges from quantum vacuum fluctuations near event horizons, where intense gravitational fields separate virtual particle pairs into real particles, with negative energy particles falling into the black hole, while positive energy particles escape as thermal radiation. The information paradox emerged when detailed analysis revealed that Hawking radiation appears completely thermal and random, carrying no information about the specific quantum states that fell into the black hole during its formation and growth. If black holes eventually evaporate completely through Hawking radiation emission, and if this radiation contains no information about infallen matter, then quantum information would be destroyed when black holes evaporate, violating the fundamental quantum mechanical principle of unitarity. Recent theoretical work has revealed that resolving the information paradox requires revolutionary changes in our understanding of event horizon physics. Rather than smooth geometric boundaries, event horizons might be dynamic quantum systems where information processing, energy generation, and spacetime geometry interact in ways that preserve quantum information while creating exotic phenomena that transcend classical gravitational physics. The firewall hypothesis, proposed by physicists including Ahmed Al-Mahiri and James Sully, suggests that event horizons might be surrounded by walls of high energy, radiation that would incinerate anything attempting to cross the horizon boundary. This firewall emerges from quantum entanglement relationships between Hawking radiation and black hole interior states that become inconsistent with smooth horizon geometry when quantum information preservation requirements are enforced. According to firewall theory, the information preservation mechanisms required to resolve the information paradox necessarily create high-energy quantum field configurations near event horizons that manifest as intense radiation barriers. Observers falling into black holes would encounter these firewalls rather than smoothly crossing horizon boundaries, experiencing violent interactions with quantum fields rather than peaceful freefall toward central singularities. Alternative resolutions to the information paradox include wormhole models where black hole interiors connect to other cosmic regions through Einstein-Rosen bridges that enable information preservation through geometric channels rather than quantum information processing. In these models, matter and information falling into black holes emerge in other cosmic locations, making black holes into cosmic transportation systems rather than information destroyers. The ER equals EPR correspondence developed by Leonard Susskind and Juan Maldacena proposes that Einstein-Rosen bridges, wormholes, are mathematically equivalent to Einstein-Podolsky-Rosen correlations, quantum entanglement, suggesting that quantum entanglement might be mediated by microscopic wormholes that connect entangled particles through spacetime geometry rather than mysterious instantaneous correlations. Applied to black hole physics, this correspondence suggests that quantum entanglement between infalling matter and external Hawking radiation might be mediated by wormhole connections that preserve information through geometric channels. Black holes would become nodes in cosmic wormhole networks that enable information flow across cosmic scales while maintaining quantum mechanical consistency through geometric rather than quantum information processing mechanisms. The holographic principle provides another framework for understanding event horizon physics by suggesting that black hole interiors are emergent phenomena that arise from quantum information processing on event horizon surfaces. In this holographic view, three-dimensional black hole physics emerges from two-dimensional quantum field theory operating on horizon boundaries, making event horizons into fundamental information processing systems rather than passive geometric boundaries. Holographic black hole models predict that information falling into black holes becomes encoded in quantum field configurations on event horizon surfaces where it can be preserved and eventually retrieved through Hawking radiation that carries subtle quantum correlations encoding complete information about infallen states. This holographic information storage enables black holes to preserve quantum unitarity while appearing to destroy information from external classical perspectives. The computational implications of event horizon physics suggest that black holes might operate as natural quantum computers with information processing capabilities that exceed any conceivable conventional technology. The quantum field dynamics on event horizon surfaces might perform calculations about gravitational physics, cosmic evolution, or quantum information processing that enable black holes to serve as cosmic computational resources. Recent developments in quantum error correction have revealed that holographic quantum systems naturally implement quantum error correction codes that protect quantum information against environmental decoherence. Black hole horizons might operate as quantum error correction systems that preserve information about infalling quantum states while enabling information recovery through sophisticated quantum information protocols. The observational signatures of exotic event horizon physics remain largely theoretical, though gravitational wave astronomy has begun providing direct observations of black hole merger events that might carry information about horizon dynamics and quantum effects. The LIGO and Virgo gravitational wave detectors have observed dozens of black hole mergers, revealing gravitational wave signals that encode information about black hole spins, masses, and possibly exotic horizon physics. Future gravitational wave observations might detect signatures of firewall phenomena, wormhole connections, or holographic information processing through subtle deviations from classical general relativity predictions in gravitational wave signals from black hole mergers. These observations could provide the first direct evidence for quantum gravity effects operating at macroscopic scales in astrophysical systems. The relationship between event horizon physics and cosmic horizon physics suggests deep connections between black hole information processing and cosmic information processing that operate through similar holographic mechanisms. Both types of horizons might encode information about their enclosed regions while processing this information, according to quantum field theory principles that transcend classical gravitational physics. The network effects of multiple black holes and cosmic horizons might create distributed information processing systems that span cosmic scales, while enabling information flow across cosmic boundaries through quantum entanglement networks mediated by wormhole connections. These cosmic information networks could process information about cosmic evolution while enabling communication across cosmic scales that would otherwise be limited by light-speed causality constraints. The implications for consciousness and information processing suggest that event horizon physics might provide mechanisms for preserving conscious information across black hole encounters or cosmic evolution events that would otherwise terminate biological consciousness. If consciousness represents quantum information processing, then horizon-based quantum information preservation might enable consciousness survival through cosmic transitions. Advanced civilizations might potentially exploit event horizon physics for computational purposes, energy extraction, or cosmic communication through technologies that interface with black hole quantum information processing systems. These applications would require sophisticated understanding of quantum gravity, holographic principles, and exotic matter manipulation that remain far beyond current technological capabilities. The philosophical implications of event horizon physics challenge assumptions about information, reality, and the fundamental nature of spacetime by revealing that cosmic boundaries might be active information processing systems rather than passive geometric structures. Event horizons become interfaces between different physical regimes rather than simple boundaries between accessible and inaccessible regions. But event horizon physics raises fundamental questions about the relationship between quantum mechanics, gravity, and information processing at cosmic boundaries. How do quantum effects create firewalls or preserve information through holographic mechanisms? What determines whether event horizons operate as barriers, transportation systems, or information processors? How do these exotic horizon phenomena relate to other cosmic boundary physics? Chapter 3. The Planck scale boundary at the unimaginably small scale of y-35 meters and 10 to 43 seconds. Spacetime itself reaches its fundamental quantum limit where classical concepts of continuous space and time break down completely, revealing what might be the most fundamental cosmic edge of all. The Planck scale boundary, where quantum gravity effects dominate physics and where space and time themselves emerge from more basic quantum geometric relationships that transcend our everyday understanding of physical reality. The Planck scale represents the convergence point where quantum mechanics, general relativity, and thermodynamics meet to define fundamental limits on measurement, causality, and information processing that apply throughout the universe. At distances shorter than the Planck length, the quantum uncertainty in spacetime geometry becomes comparable to the geometrical structures themselves, making classical concepts of spatial distance and temporal duration meaningless. The mathematical definition of Planck units emerges from combining fundamental physical constants, including the speed of light, Newton's gravitational constant, and Planck's quantum constant in ways that create natural units of length, time, mass, and energy. The Planck length equals approximately 1.6 times 10 to 35 meters, while the Planck time equals approximately 5.4 times y-44 seconds, representing the smallest spatial and temporal intervals that can have operational meaning within known physics. At the Planck scale, quantum fluctuations in spacetime geometry become so intense that the usual distinction between matter and geometry disappears, with quantum fields and spacetime curvature becoming different aspects of the same underlying quantum geometric reality. Space and time might exist only as emergent statistical phenomena that arise from more fundamental quantum information, processing mechanisms operating at sub-Planck scales. Loop quantum gravity provides one theoretical framework for understanding Planck scale physics by treating spacetime as a discrete quantum structure built from elementary quantum geometric building blocks called spin networks. In this approach, space consists of finite quantum volume elements connected through quantum geometric relationships that replace continuous classical spacetime with discrete quantum geometry. The implications of loop quantum gravity include predictions that black hole singularities are replaced by quantum geometric transitions that connect black hole interiors to other cosmic regions through quantum wormhole mechanisms. These quantum geometric transitions might enable information and matter to pass through black hole centers while avoiding the infinite curvatures predicted by classical general relativity. String theory offers an alternative approach to Planck scale physics by proposing that fundamental particles are excitations of one-dimensional strings vibrating in 10 or 11-dimensional spacetime. At the Planck scale, string theory predicts that additional spatial dimensions become observable while creating exotic physics, involving extended objects, topological solitons, and higher-dimensional membrane dynamics. The extra dimensions predicted by string theory might become accessible at Planck scale energies while remaining compactified, and invisible at lower energy scales that characterize ordinary physics. These extra dimensions could contain exotic physics, alternative forms of matter and energy, or connections to other cosmic domains that remain hidden from conventional observations. Causal set theory proposes that spacetime consists of discrete events connected by causal relationships, with space and time emerging from statistical properties of these fundamental causal networks. At the Planck scale, this discrete causal structure would become apparent while revealing that continuous spacetime represents an approximation that breaks down when examined at sufficient resolution. The holographic principle takes on new meaning at Planck scale boundaries by suggesting that three-dimensional physics might emerge from two-dimensional quantum information processing operating on Planck scale boundary surfaces. This could make Planck scale boundaries into fundamental information processing interfaces, where quantum information creates the appearance of higher dimensional physics through holographic projection mechanisms. Quantum foam models propose that spacetime at the Planck scale resembles a foaming quantum structure where virtual particles and spacetime fluctuations create rapidly changing geometric configurations that average out to smooth spacetime geometry on larger scales. This quantum foam might contain exotic physics, including spontaneous particle creation, microscopic black holes, and quantum wormhole networks. The information processing implications of Planck scale physics suggest that quantum geometric structures might operate as natural computational systems that process information about cosmic evolution, physical laws, and possibly consciousness itself. The quantum geometric networks that compose spacetime might perform calculations that determine physical constants, natural laws, and cosmic evolution patterns. These Planck-scale computational processes might operate according to quantum algorithms that transcend classical computational limitations while enabling information processing capabilities that approach theoretical limits determined by quantum mechanics and thermodynamics. Spacetime itself might be a cosmic computer that calculates its own evolution through quantum geometric information processing. The emergence of classical physics from Planck-scale quantum geometry requires sophisticated understanding of how quantum geometric networks create the appearance of continuous spacetime through statistical averaging over quantum fluctuations. The transition from discrete quantum geometry to continuous classical geometry might involve phase transitions similar to those that occur in condensed matter physics. The cosmological implications of Planck-scale physics include predictions about cosmic inflation, dark energy, and cosmic evolution that might be determined by quantum geometric processes operating at fundamental scales. Cosmic inflation might emerge from Planck-scale quantum geometric dynamics, while dark energy might represent quantum geometric effects that influence cosmic expansion rates. Consciousness and Planck-scale physics raise speculative possibilities about quantum geometric foundations for awareness and information processing that might transcend biological neural networks. If consciousness involves quantum information processing, then the quantum geometric networks that compose spacetime might provide substrates for consciousness that operate at fundamental physical scales. The experimental accessibility of Planck-scale physics remains extremely challenging because the energies required to probe Planck-scale effects exceed those achievable in any conceivable particle accelerator by enormous factors. However, indirect signatures of Planck-scale physics might be observable through cosmic phenomena, including gravitational waves, cosmic ray interactions, and quantum cosmological effects. Gravitational wave astronomy might provide the most promising avenue for detecting Planck-scale physics signatures through observations of black hole mergers, neutron-star collisions, and possibly primordial gravitational waves from cosmic inflation that could carry information about Planck-scale quantum geometric dynamics operating during the universe's earliest moments. Black hole evaporation through Hawking radiation might provide another window into Planck-scale physics by revealing quantum geometric effects that operate during the final stages of black hole evaporation, when black hole masses approach Planck-scale values. These observations might reveal transitions from classical black hole physics to quantum geometric physics. The technological implications of Planck-scale physics might include quantum geometric engineering techniques that enable manipulation of spacetime structure for applications, including faster-than-light communication, energy extraction from vacuum fluctuations, and possibly consciousness preservation through quantum geometric information processing mechanisms. Future theoretical developments in quantum gravity string theory and related approaches to Planck-scale physics might reveal new principles of quantum geometric information processing that enable unprecedented computational capabilities, communication technologies, and possibly artificial consciousness systems based on quantum geometric substrates rather than biological neural networks. The philosophical implications of Planck-scale physics challenge fundamental assumptions about the nature of space, time, matter, and consciousness by revealing that familiar physical reality might be emergent phenomena arising from more fundamental quantum geometric information processing. This could make consciousness, physical laws, and cosmic evolution different aspects of cosmic computational processes. The unity of physics at Planck-scale boundaries suggests that quantum mechanics, gravity, thermodynamics, And information theory might be different aspects of more fundamental quantum geometric principles that operate at the ultimate boundaries of physical reality. Understanding Planck's scale physics might reveal the fundamental computational structure that underlies all physical phenomena. But Planck's scale physics raises profound questions about the relationship between discrete quantum geometry and emergent continuous reality. How do quantum geometric networks create the illusion of continuous spacetime? What determines the specific quantum geometric structures that underlie our observable physics? How do quantum geometric information processing mechanisms relate to consciousness and cosmic evolution? Chapter 4. Cosmic inflation during the universe's first fraction of a second. Cosmic inflation stretched space exponentially, taking quantum scale fluctuations and enlarging them to cosmic proportions, while creating the most dramatic example of physics operating at cosmic boundaries, where spacetime expansion exceeds light speed and where quantum effects dominate cosmic evolution. This inflationary epoch reveals how cosmic edges can be created dynamically through extreme spacetime dynamics that transcend classical causality constraints while enabling quantum information processing on cosmic scales. The theoretical framework of cosmic inflation addresses fundamental problems in Big Bang cosmology by proposing that the early universe underwent exponential expansion driven by quantum scalar fields trapped in unstable vacuum configurations. During inflation, space expanded by factors exceeding 1026 within time intervals shorter than 10 to 32 seconds, creating cosmic evolution rates that dwarf any subsequent cosmic processes while establishing initial conditions for conventional cosmic evolution. The physics of inflationary expansion operates through mechanisms that violate everyday intuitions about spatial expansion and energy conservation. Unlike normal expansion, where energy density decreases as space grows larger, inflationary expansion maintains constant energy density through continuous creation of space and matter from quantum vacuum fluctuations. This apparent violation of energy conservation is permitted by general relativity in expanding spacetime configurations. The quantum field dynamics driving inflation involve scalar fields called inflatons that evolve according to quantum field equations in curved spacetime. When inflaton fields become trapped in false vacuum states with high energy densities, they drive exponential cosmic expansion through negative pressure effects that create repulsive gravitational forces. This continues until quantum tunneling or classical field evolution enables transition to lower energy states. The end of inflation occurs through reheating processes where inflaton field energy converts into ordinary matter and radiation through particle creation mechanisms that establish initial conditions for hot Big Bang cosmology. The timing and efficiency of reheating determine the cosmic microwave background temperature, light element abundances, and other observable features of cosmic evolution. The boundaries of inflationary regions represent some of the most extreme cosmic edges imaginable, where exponential spacetime expansion creates horizons that isolate causally connected regions while enabling faster-than-light recession velocities between different spatial locations. These inflationary horizons operate as information barriers that prevent communication between different cosmic domains while enabling independent cosmic evolution. Eternal inflation theory predicts that inflation never ends globally, but continues indefinitely in most spatial regions while terminating locally to create causally disconnected cosmic domains like our observable universe. This creates infinite cosmic landscapes containing every possible combination of physical parameters, initial conditions, and evolutionary histories, while making our cosmic domain infinitesimal within the broader inflationary multiverse. The quantum fluctuations during inflation create the seeds for all subsequent cosmic structure formation by stretching microscopic quantum uncertainty to macroscopic scales. These quantum fluctuations generate density perturbations that eventually grow through gravitational collapse to form galaxies. Galaxy clusters and large-scale cosmic structure while preserving quantum statistical properties on cosmic scales. The statistical mechanics of inflationary quantum fluctuations involve sophisticated treatments of quantum field theory and rapidly expanding spacetime that reveal how quantum uncertainty becomes cosmic structure through stochastic processes that operate during exponential expansion. These quantum to classical transitions create cosmic structure through mechanisms that transcend conventional thermodynamic evolution. The multiverse implications of eternal inflation suggest that cosmic boundaries created during inflation separate infinite numbers of causally disconnected cosmic domains with potentially different physical laws, fundamental constants, and evolutionary histories. Our observable universe represents one small bubble within infinite inflationary space where local physics might be unrepresentative of typical cosmic conditions. The anthropic principle takes on new significance within inflationary multiverse contexts because observers can only exist within cosmic domains where physical parameters permit complexity and consciousness development. This selection effect might explain apparent fine-tuning in physical constants through environmental selection rather than fundamental physical necessity, making our cosmic domain atypical within the broader multiverse. The information processing implications of inflationary cosmic boundaries include quantum computational processes that might operate during inflation to determine subsequent cosmic evolution patterns. The quantum field dynamics during inflation might perform calculations about optimal cosmic parameter values while implementing cosmic evolutionary algorithms that explore different possibilities for cosmic development. The energy extraction possibilities from inflationary boundaries involve exploiting the negative pressure effects that drive exponential expansion for technological applications, including faster-than-light propulsion, infinite energy generation, and cosmic engineering projects that manipulate space-time geometry on cosmic scales. These applications would require mastery of quantum field manipulation in curved spacetime. The causal structure of inflationary boundaries creates opportunities for information transmission that transcends conventional light speed, limitations through quantum entanglement networks that might be established during inflation. Quantum correlations created during inflation might enable instantaneous information transmission across cosmic scales while bypassing causal horizon constraints. The observational signatures of inflationary boundary physics include gravitational wave backgrounds created by quantum fluctuations during inflation, cosmic microwave background polarization patterns that encode information about inflationary quantum dynamics, and possibly detectable signatures of cosmic domain boundaries within our observable universe. The Planck satellite observations of cosmic microwave background anisotropies have provided increasingly precise measurements of inflationary predictions while constraining inflationary models and revealing detailed information about quantum processes operating during cosmic inflation. These observations confirm inflationary predictions while enabling precision tests of quantum field theory in curved spacetime. Future gravitational wave observatories might detect primordial gravitational waves created during inflation through quantum fluctuations in spacetime geometry. These observations would provide direct evidence for quantum gravity effects operating during inflation while revealing information about Planck scale physics that operated during the universe's earliest moments. The technological implications of understanding inflationary boundary physics might include artificial inflation technologies that enable controlled spacetime expansion for applications including space travel, energy generation, and cosmic engineering. These technologies would require manipulation of quantum scalar fields and spacetime geometry that exceeds current technological capabilities by enormous factors. The relationship between inflationary boundaries and consciousness raises speculative possibilities about cosmic Awareness operating through quantum information processing networks established during inflation. If consciousness involves quantum information processing, then inflationary quantum networks might provide cosmic substrates for awareness that transcend biological neural systems. Advanced civilizations might potentially exploit inflationary boundary physics for cosmic engineering applications, including universe creation, cosmic parameter manipulation, and possibly consciousness preservation through cosmic transitions that enable survival across cosmic domain boundaries. These applications would require technological capabilities approaching those of cosmic inflation itself. The philosophical implications of inflationary boundary physics challenge assumptions about uniqueness, causality, and the relationship between local physical experience and cosmic reality. If inflation creates infinite cosmic domains with varying physics, then our local physical laws might be environmental rather than fundamental, while cosmic reality transcends any individual cosmic domain. The cosmic democracy of inflationary boundaries suggests that no cosmic domain possesses special status within the inflationary multiverse, making our observable universe one of infinite variations, while creating cosmic contexts where every possible form of physics and consciousness exists somewhere within infinite inflationary space. The ultimate questions raised by inflationary boundary physics extend to fundamental issues about the nature of physical law, cosmic evolution, and consciousness within cosmic contexts where infinite variation creates every possible cosmic environment. How do we understand physical truth when physics varies across cosmic domains? What does individual significance mean within infinite cosmic variation? How do we comprehend cosmic purpose when every possible cosmic evolution occurs within inflationary multiverse? But inflationary boundary physics also reveals elegant mathematical principles of quantum field theory in curved spacetime that might represent universal truths transcending individual cosmic domains. The quantum statistical processes that operate during inflation might implement cosmic natural selection mechanisms that favor cosmic domains, capable of supporting complexity and consciousness while creating cosmic evolution toward increased information processing capabilities. Understanding inflationary boundary physics might ultimately reveal that cosmic evolution operates through quantum computational processes that explore cosmic possibility space while enabling consciousness development through cosmic environments, optimized for awareness and intelligence. Inflationary boundaries become interfaces between cosmic computational domains rather than simple spatial separations. Chapter 5. The holographic boundary. One of the most revolutionary insights in modern physics suggests that all information contained within any cosmic volume can be encoded on its boundary surface, making cosmic edges not empty limits, but information-dense interfaces that contain complete descriptions of everything within their enclosed regions. This holographic principle transforms our understanding of cosmic boundaries from passive geometric structures into active information processing systems that might represent the fundamental computational architecture underlying physical reality itself. The mathematical foundation of the holographic principle emerged from black hole thermodynamics. Studies revealing that black hole entropy scales with horizon area rather than enclosed volume, suggesting that gravitational systems store information on their boundaries rather than within their interiors. This area law for entropy implies that three-dimensional physics might be emergent phenomena arising from two-dimensional information processing on boundary surfaces. Jacob Bekenstein's pioneering work on black hole thermodynamics established that black hole entropy equals 1/4 of the horizon area measured in Planck units, providing the first evidence that gravitational systems might operate according to holographic principles. This Bekenstein bound represents the maximum information storage capacity for any spatial region, making black hole horizons into the densest possible information storage systems while suggesting holographic organization of cosmic information. The IDCFT correspondence, discovered by Juan Maldacena, provides concrete mathematical realization of holographic principles by demonstrating exact equivalence between gravitational theories in anti-de Sitter spacetime and conformal field theories operating on the boundary surfaces. This holographic duality reveals that gravitational physics within cosmic regions corresponds precisely to quantum field theory on cosmic boundaries. The implications for cosmic boundary physics include predictions that three-dimensional gravitational interactions emerge from two-dimensional quantum information processing while maintaining exact mathematical equivalence between bulk and boundary descriptions. This makes cosmic edges into fundamental information processing interfaces rather than derived geometric structures, while suggesting that familiar three-dimensional physics might be holographic projections. The information processing capacity of holographic boundaries approaches theoretical limits determined by quantum mechanics and thermodynamics. Holographic boundaries can store approximately 1 bit of information per Planck area, making cosmic boundary surfaces into cosmic hard drives with storage capacities exceeding any conceivable conventional technology, while enabling information processing operations that transcend classical computational limitations. The quantum error correction aspects of holographic systems provide mechanisms for protecting quantum information against environmental decoherence while maintaining information accessibility through sophisticated quantum information protocols. Holographic boundaries naturally implement quantum error correction codes that enable information preservation and recovery through distributed quantum information processing across boundary surfaces. The emergence of spacetime geometry from holographic information processing suggests that familiar three-dimensional space might be computed through quantum information processing on two-dimensional boundary surfaces. Spacetime curvature, gravitational forces, and matter distributions might represent different aspects of quantum information processing algorithms, operating on holographic boundaries rather than fundamental features of three-dimensional reality. The computational implications of holographic boundaries include possibilities for quantum information processing that approaches theoretical limits while enabling calculations about cosmic evolution, physical laws, and possibly consciousness that would be intractable using conventional computational approaches. Holographic boundaries might operate as cosmic computers that calculate reality through quantum information processing. The network effects of multiple holographic boundaries suggest distributed information processing systems that span cosmic scales while enabling information sharing and coordination across cosmic regions. These holographic networks might process information about cosmic evolution while implementing cosmic natural selection mechanisms that guide cosmic development toward increased information processing capabilities. The relationship between holographic boundaries and consciousness raises profound questions about the computational nature of awareness and its relationship to cosmic information processing systems. If consciousness represents information processing, then holographic boundaries might provide cosmic substrates for awareness that transcend biological neural networks while enabling consciousness persistence through cosmic transitions. The observational testing of holographic principles remains challenging because holographic effects typically operate at Planck scales or cosmic horizon scales that are difficult to probe directly. However, precision tests of gravitational physics, black hole dynamics, and cosmic evolution might reveal signatures of holographic information processing through subtle deviations from classical gravitational predictions. Quantum simulation experiments using condensed matter systems have begun implementing holographic dualities in laboratory settings, enabling direct study of holographic information processing mechanisms while testing theoretical predictions about quantum error correction, information scrambling, an emergence of classical physics from quantum information processing. The technological applications of holographic principles might include quantum information processing systems that exploit holographic error, correction for computational applications, communication systems that use holographic boundary effects for information transmission, and possibly consciousness preservation technologies based on holographic information storage and processing. Advanced civilizations might develop technologies that interface directly with cosmic holographic boundaries for applications, including cosmic information access faster than light, communication through quantum information, networks, and cosmic engineering applications that manipulate reality through holographic boundary control rather than direct matter and energy manipulation. The multiverse implications of holographic boundaries suggest that cosmic domains separated by holographic boundaries might share information through quantum information processing networks that transcend conventional spatial separation. These holographic networks might enable communication and coordination across cosmic domain boundaries while maintaining information consistency across multiverse regions. The philosophical implications of holographic boundary physics challenge fundamental assumptions about the nature of three-dimensional reality by revealing that familiar spatial experience might be emergent, phenomena arising from more fundamental two-dimensional quantum information processing. This could make consciousness, matter, and spacetime different aspects of cosmic computational processes. The information-theoretic foundations of reality suggested by holographic principles imply that physics might be fundamentally computational rather than mechanical, with physical laws emerging from quantum information processing algorithms rather than fundamental force relationships. This computational view of physics makes information processing primary while treating matter and energy as secondary computational products. The unity of physics and information theory at holographic boundaries suggests that quantum mechanics, gravity, thermodynamics, and consciousness might be different aspects of cosmic information processing, systems that operate through holographic principles. Understanding holographic boundaries might reveal the fundamental computational architecture that underlies all physical phenomena, while unifying previously separate aspects of physics. The causal structure of holographic boundaries creates opportunities for information processing that transcends conventional spacetime limitations through quantum information networks that operate according to holographic dualities. These quantum networks might enable information transmission and computational coordination that bypasses classical causality constraints while maintaining consistency with relativistic physics. The emergence of complexity from holographic boundaries involves sophisticated quantum information processing mechanisms that create the appearance of three-dimensional complexity through two-dimensional quantum algorithms. The evolution of galaxies, stars, planets, and biological systems might represent different computational outputs from holographic boundary information processing rather than independent physical developments. The cosmic democracy of holographic boundaries suggests that all cosmic regions possess equivalent holographic information processing capabilities while contributing equally to cosmic computational networks. No cosmic domain enjoys special information processing privileges, making cosmic evolution a democratic computational process where every boundary contributes to cosmic information processing. The ultimate implications of holographic boundary physics suggest that understanding cosmic edges might be equivalent to understanding the computational structure of reality itself. Cosmic boundaries become interfaces in cosmic computers rather than spatial limits, making edge physics equivalent to computational physics while revealing consciousness, matter, and cosmic evolution as different aspects of cosmic computational processes. But holographic boundary physics raises fundamental questions about the relationship between information processing and physical reality. How does two-dimensional information processing create three-dimensional spatial experience? What determines the specific holographic algorithms that compute our observed physics? How do quantum information processing mechanisms create the appearance of matter, energy, and consciousness from pure information processing?